All right, let's get started. As you can see from last week's lecture and the homework, we are going through some more and more theoretical stuff, right? And if you think last week's lecture is a lot of mathematics, today we are actually going to ramp up how mathematical the aerodynamics is becoming, because if you think previously we have been mostly using single variable calculus, right? I mean, even the sensitivity analysis has been really just looking at streamlines along X. So today we are going to introduce the concept of vorticity and focus on it. And whenever you look at vorticity, it's going to be a multivariate calculus, right? I mean, there is no vorticity in one-dimensional flow. All right, so basically we have really quickly went through some applications of aerodynamic forces and drag and energy consumption. So basically doing some control volume stuff to really emphasize what we are looking at, lift and drag, and why we are looking at lift and drag. Okay, and then to actually go to the next section of diving into details of the mechanism of how air is moving and therefore generates the lift and drag, we need to first go through some theoretical stuff. So we have first of all analyzed flow regimes, and in the process introduced the very powerful tool of fractional sensitivity analysis, right? The end result of that is we derived the Mach number and the Reynolds number, and that really defines the different flow regimes. And that also defines what we are going to be looking at next. That is incompressible, meaning low Mach number, well, low squared Mach number. And also incompressible and the potential flow. So potential flow means high Reynolds number, but also a lack of vorticity, right? So that is what we are going to be looking at next, is what is vorticity and exactly what defines a potential flow, even in the context of high Reynolds number. And that is really the chart we went through last. So when we have general compressible viscous flow, if we are assuming high Reynolds number, we get to the regime of compressible but inviscid flow. But in order to get potential flow, we want to assume the addition of zero vorticity in the flow field, right? And also, if you go from compressible viscous flow, you assume low Mach number, you get incompressible, right, low Mach number, and viscous flow. And this is really because the fractional sensitivity of density with respect to a change in velocity is proportional to Mach squared, right? So if Mach squared is small, you can assume the density doesn't change as velocity increases or decreases. You get incompressible flow. And then in addition, you assume high Reynolds number, you get incompressible and inviscid flow. Again, we need to assume this zero vorticity to get to incompressible potential flow, which is what we are going to be discussing really in the second portion of 16100. Okay, so why we're assuming this zero vorticity and what exactly is vorticity? That's the topic of this lecture. Okay, so we're going to, as I said, dive into a lot of multivariate calculus. But before that, let's just watch some videos and make an intuitive understanding of what is vorticity. So let's actually watch some vorticity going on, right? So this is basically a collection of airplanes flying by where there happens to be cloud in the sky that helps visualize how the surrounding air moves. I mean, this is actually very similar to what you see in Top Gun 2 when the airplane pulls up and you get the air flowing. But in this case, we actually see more details of what is happening. You see this very thin strip of cloud, right? And here, as it moves through the cloud, you see really a core of vortex over here and how the surrounding air is moving. Right, the air basically getting pushed downwards in this region. That is very similar to what we see. But here we have the and you see this coming from basically the again, concentrated line of vorticity. And watch how the vorticity, how the vortex moves, and also how the surrounding air moves here where the vortices are. It's maybe hard to see over here, but there are vortices over again coming out of the junction between where the flaps are and where there are no flaps. There has to be ailerons right at the end, so you cannot put flaps near the tips. And now you can see very clearly how the air is moving right in between these two vortices. And usually when you see cloud, that is regions of, why do you see cloud actually, right? Why do you see a water vapor in some regions, but the air is transparent in other regions? Anybody has any idea? Yes?
When the air is like being vortex a lot, the density would change, the point would change, so it's a lot for the moisture.
Exactly. So the reason you see the moisture being visualized is because there is condensation, and there is condensation because the temperature actually over there is lower than the temperature in surrounding regions. Actually, both temperature and the pressure. So air is being expanded in the region where you see moisture condensation, right? And the reason there is, so basically what you are watching is regions of low pressure, and as a result also low temperature, because as you are expanding air to low pressure, you get the temperature actually drops, right? So basically today we are going to be looking mathematically on, first of all, where is there vorticity, where there is no vorticity, and second of all, when there is no vorticity, how does air move? And the third is when there are regions where there is vorticity and other regions where there is no vorticity, how does air move around it? Right, so basically this is a case where there is vorticity coming out of here, but there are also large regions of the flow where there is no vorticity, right? And we want to be able to derive, first of all, how would the air move when there is no vorticity around? And two is how does vorticity actually, what equation does vorticity follow? And the third, how does air move around these vorticities? And let me see if I can go to the end where there is another very good, very nice shot on how the air. So when you think of the airplane pushing air down or sucking air down or moving air down, right? This is how the air actually moves. As you can see, it is not exactly like what we did in the homework. It just pushes down a cylinder. Actually, the air moves in a large region around it. It's just in between these two vortices, the air is set to move in a much higher speed than everything else. Okay, if you go to YouTube, there are plenty of such videos for you to watch. Just search for planes and vortices. So today we are going to be spending most of the time looking at what is vorticity mathematically. And to make things easier, we are first going to look at two dimensions, so just the x and y. Okay, vorticity is really regarding to how the flow is deforming. So assuming I have a flow field, okay, and let's say I put, let's say I'm able to somehow magically inject some dyes in the air so that I get a colored, let's say a red colored rectangle. Actually, let me actually, instead of using rectangle, let me use a cross. Okay, if you read Anderson's book, there is a very detailed analysis of what happens to a rectangle. So here, I'm going to use a cross instead. So that you get a complementary information on what is vorticity. All right. So let's imagine after a while, after a little bit, let's say 1 second or 0.1 second, this cross has moved to somewhere else. Is it generally true in a fluid that this cross is going to stay as a cross? Yes or no? No, right? Because it's a fluid. If it's a solid, it'll stay across. But if it's fluid, it doesn't. So imagine if the cross is very, very small, then there is really a limited number of motions this cross can actually go across, right? So first of all, let's look at the horizontal line. The horizontal line, actually, let's color them differently. Let's color the horizontal line as red and the vertical line as green, so that we actually have better visualization of what's going on. So the first thing this red line can do is to lengthen or shorten, right? In a fluid, it doesn't. A line doesn't have to stay exactly the right length. So it can become longer, it can become shorter, right? So that's one motion. The other possible motion is the red line can tilt up or down. And that's actually the only two things this can do. If the line is short enough, right? If the line is very long, it can curve and do various fancy things. But if the line is very short, it's like the curvature is not visible anymore. It's like the Earth is curved, but because we are very small compared to the Earth, we don't see the curvature, right? So if the lines are very small, the only thing it can do is to either be is actually to do two things simultaneously. One is becoming shorter or longer, and the other is tilt a little bit. Okay, the green line can do exactly the same set of things. It can become longer or shorter, and it can tilt a little bit. So let's imagine the green line tilts like that. Vorticity is defined as the angle at which the red line tilts plus the angle the green line tilts, but in the opposite direction. So vorticity is defined as, let's say, the angle theta red plus this angle theta green, okay? So it's theta red plus theta green divided by this small amount of time. So that's what vorticity is. Okay, so from this definition, it is already useful in some sense because it actually gives you a way to measure vorticity experimentally. Why is that the case? Because you can actually build a cross, very small cross, an infinitesimal cross, and put it in the flow field. And imagine if the cross is made of solid, it's rigid as opposed to be made of a fluid dye. What happens is that the fluid, the red portion of the fluid is trying to push the cross to rotate in a counterclockwise direction, but the green fluid is going to try to push the cross to move in a clockwise direction, right? And whichever force, whichever one deforms at a higher angle per unit time, it is going to exert a higher force on this solid cross and therefore wins, right? So, for example, if the vorticity is exactly 0, actually the angles are Yes. So if the vorticity is exactly 0, this actually did I put it in the wrong way? Theta in this direction, theta in this direction. It's actually minus. Sorry. This actually has to be minus. Yeah, has to be minus. Sorry. Yeah. So basically, if the vorticity is 0, then these two angles are exactly the same. Then the force exerted on the cross in the clockwise direction and in the clockwise direction and counterclockwise direction exactly cancels out. So the cross would stay exactly upright. All right, makes sense? So that is one way to think about what is vorticity, is if you put a small cross of the same length into the flow field, would it rotate in the clockwise direction or counterclockwise direction? If it rotates in one direction, the vorticity is positive, the other direction is negative, and if it doesn't rotate at all, there is no vorticity. All right, any questions on this type of way to define what vorticity is? If no, let's, yes?
Is the theta green, is it measured like that angle is measured clockwise?
Yes, right. So basically you're measuring one angle clockwise, the other angle counterclockwise, okay, right? And then you subtract these two different angles. So for example, if the green one is tilted the same way, right? If both tilt counterclockwise, then of course there is a net force that rotates this cross counterclockwise, and therefore you will get a vorticity, right? No matter what the magnitudes are. Okay. So let's get a little bit more mathematical. What is this angle exactly? Right? So if I have, let's look at the red angle first. Imagine the length of this red is dx, right? I said it's very small. Okay, then how much does it actually tilt if we have a velocity field? All right, so let's imagine the velocity field here is u v, right? So u is the velocity in the x direction, v is the velocity in the y direction. And now let's imagine the velocity here is u plus, I'm going to start using partial derivatives, right? Partial u partial x times dx, right? Because it's the flow field that is at a different location, and the different location has it has the same y but a different x, right? And v plus partial v partial x times dx. So that is the flow field. That is the velocity over here, and that is the velocity over here. All right. So after a moment, what is the angle? The angle after an infinitesimal amount of time, right? Because the angle is actually going to be very small after an infinitesimal amount of time. This angle, theta r, can be written just as the delta y of this line divided by delta x of this line, right? Okay, and what is the delta y of this line? The delta y of this line is just going to be the velocity over here times delta t minus the y velocity over here times delta t. So it is equal to the, well, let me just first write it out, delta y over delta x. That's a small angle approximation, right? Because we only a very small amount of time has passed, right? So delta y is y at the right hand minus y at the left hand. And y at the right hand is equal to, let's say this is the origin, so 0, 0 is the origin, then after a while it is going to be v plus partial v partial x dx, and then the whole thing times dt, right, minus just the v times dt. That is the delta y. Any question on that? So basically, this is how this point, the right end, how much that has moved, right? This v dt is how much this point, the left point, has moved in the y direction. Okay, now what is delta y? Well, delta y, what is delta x? Delta x is dx plus something, dx is the delta to start with, right? And plus how much this has lengthened. Now I don't need to calculate how much it has lengthened, because how much it has lengthened, just like in this formula, it is proportional to dx times dt. And as long as dt is very small, this additional term in the denominator is very small compared to dx. All right, so I can basically write it down as the limit of dt goes to 0, it is basically equal to cancel out partial v partial x dx dt, and that is basically the dx also cancels out. I have dv dx times dt. All right. Any questions? Yeah, so this is basically mathematically figuring out what is the angle of this red line. Okay, the green line, I won't do the step by step, but like you can exactly follow the same process and figure out the green line. The angle of the green line is going to be dx over dy. Okay, and that basically is going to be the same process. You're going to have u plus partial u partial y here, because the green line is aligned in the y direction. You're looking at a difference in y, minus u times dt, right, over dy plus something that is small. Okay, that'll end up to be partial u partial y times dt. So the amount of angle per unit time, or the angular velocity, right, of the red line and green line, are partial v partial x and partial u partial y, respectively. Okay, so that means when I write down this formula of omega equal to theta r minus theta g divided by dt, what I get is partial v partial x minus partial u partial y. Okay, and this quantity, this maybe you can also give some suggestion of how to write omega to distinguish it from w, right? But this is omega. What?
Little arrow on the top.
Arrow like here. Okay, that's good. Okay, so this is omega, right? And basically, it is what sense it is. By sense, I mean towards which direction, which rotational direction is this omega? Right, so because if omega is positive, right, then the red arrow wins. So it is basically rotates in this way, right? Okay, so this omega is defined as omega, defined as vorticity in the counterclockwise direction, or another way to say it, using a right-hand rule, is a vorticity that points out of this board. All right, so the sense of vorticity does matter a lot, and is actually a pretty common mistake in doing fluid mechanics. Is you messed up just a dumb mistake, just like how you mess up a sign error, right, in algebra. So the sense of the vorticity is really the sign. Okay. Any questions? No? Good. Okay. So the next question, after we figured out what is vorticity, is why is it useful, right? Why are we looking at this particular angular rotation of a solid across, right, in the flow field? Well, two reasons. Let's see. Reason one is there is a lot of cases where omega is exactly equal to 0, right, in a large portion of the flow field. And the complementary reason for that is if omega is 0, we can actually use a lot of tools. We can analyze the flow a lot better, I would say, a lot easier and a lot better. So let's first figure out why is there a lot of cases where omega is exactly equal to 0. So that actually involves a little bit more derivation. So why 1? So let's consider the momentum equation. And we are going to figure out, like, from the momentum equation, what is the governing law of omega, of vorticity. And we are going to see that if there is no vorticity to start with, okay, which is the case, right, if you consider an airplane flying at very quiet air where there is no turbulence, then the incoming air has no vorticity because it's a uniform velocity of, depending on which frame of reference you use, right? But both cases, you have no vorticity, because if you add a constant speed to the flow field, it doesn't change the derivative, right? And the vorticity only depends on the derivative of velocity with respect to x and y. So no matter what translational frame of reference you use, it doesn't change vorticity. And if you take the frame of reference of the free stream, then velocity is equal to 0 everywhere, and the vorticity therefore is equal to 0 everywhere. Okay, so if you have no vorticity to start with, and the viscous force is very small, then there is no vorticity that you end up with. That's what we are trying to derive, is that the derivative, the rate of change in vorticity in a flow field when there is no vorticity is exactly equal to 0. Okay, so let's start with the momentum equation. The momentum equation, as we have always been saying, is rho partial t, right, plus, well, the divergence of rho u, so this is a tensor product, plus a gradient of p is equal to viscous forces, right? And let's actually defer viscous forces to later, because we'll see that if there is viscous force, there is mechanism of generating vorticity. But if there are no viscous forces, right, so no viscosity. All right. So now, if there is no viscosity, do you remember that we can actually pull the rho out and use conservation of mass to get rid of it in both this term and this term, right? So essentially what we are doing is we are writing this as partial rho partial t times u plus rho times partial u partial t. So, and the second term as divergence of rho u times velocity, right? And plus rho u dot with the gradient of velocity, right? So basically we can write this term and this term separately, okay? And that is equal to 0. And if you're using conservation of mass, you're going to see this term plus this term is exactly 0 because of conservation of mass. And as a result, you're only left with these terms. And this can be written as if you divide the density on both sides. If you're dividing density on both sides, what you get is du dt plus u dot with grad u plus 1 over rho grad p is equal to 0, right? So we'll derive our governing law of vorticity from this equation. Okay. Of course, this equation can be written as two equations. So let's actually do it very carefully using no notations like no notations like taking no like vector calculus notations like gradient and divergence and curl, right? So let's do it slowly to see if we can. Yeah. So we'll try not to use these more fancy calculus tools and do it very slowly. So this equation basically means two equations. One is the derivative of ux. Actually, let me just use consistently u and v. So the u with the vector sign means u and v. The u without the vector sign just means x velocity. All right, and the v means the y velocity. So that means this plus u times d dx of u plus v times du dy, right? So this is what we mean by u dot with the gradient. The gradient can be written as d dx and d dy as a vector, right? So u times d dx plus v times d dy is what we mean by u dot with the gradient. And that is plus 1 over rho times dp dx is equal to 0. So that's the x direction momentum equation. And the y directional momentum equation is very similar. dv dt plus u dot with dv dx, right? Plus v dot with dv dy plus 1 over rho dp dy is equal to 0. So these are what the black equation actually mean if you write it component by component. Okay, what we'll be doing next is to combine these two equations to form vorticity. Remember, what is vorticity? Vorticity, let me make it a little bit thicker. Vorticity is partial v, partial x, minus partial u, partial y, right? It's a bit too thick. So what we're going to be doing is we are going to take d dx to the entire second equation and subtract it with d dy of the entire first equation. All right, we are going to take d dx on this one and we'll take d dy on this one and then subtract it. Well, okay, and you're going to see, because in multivector calculus, the partial derivatives actually exchange with each other. They commute, right? So d dx of dv dt is going to be equal to d dt of dv dx, right? That's one of the I don't know, first things you learn in multivariate calculus, I believe, right? Okay, so basically this first term actually combines into the partial derivative of omega itself. All right, make sense? And this term is quite interesting. So this term, when you are considering general compressible flow, actually, when you take the derivatives, it will not become zero, right? Because density actually varies. But if you are considering an incompressible flow where density is constant, okay, what you get is ddx of, the 1 over rho can be pulled out, right? It is constant. So what you get is 1 over rho times the second derivative of p with respect to both x and y, and then subtract with, again, the second derivative of p with both x and y. So in an incompressible flow, the pressure term also contributes to nothing to vorticity. Now the only thing you remain is this, right? So let's actually see, well, let me see, this is equal to 0 for constant rho, rho, not p. All right, so let's just consider the what we call convection term for the velocity. So let's look at the first line first. So what we get is minus d dy of u du dx. Again, minus d dy of v du dy. And then for the red, we have plus d dx of u du dx, dv dx. dv dx. Sorry, this was not clear. Okay, and then plus d dx of v dv dy. All right. Any questions so far? Right, I'm just basically taking derivative of these two terms. Now, each of these derivatives can be split into two terms. For example, the first derivative can be split into du dy times du dx plus u times the second derivative of u with respect to both x and y, right? Okay, so let's actually let's actually write them independently. So let's split all of these into these actually two parts. So let's first carry out d omega dt, right? And let's just write out the first part. And the first part is du dy du dx minus dv dy du dy, right? And for the red is plus du dx dv dx, and then plus dv dx. I don't know why it keeps doing that. dv dy. Right? And then we have the second part. The second part is minus u times second derivative of u with respect to x and y minus v times the second derivative of u with respect to y squared. And we have plus u times the second derivative v with respect to x squared minus v times the second derivative of v with respect to x and y. Okay, so let's first take a look at this. What is the first column added together? We have du dx in the common term, right? Now, the other non-common term is dv dx minus, oh, sorry, that's actually not the right way to combine it. Oh, yeah, that is the right way to combine it, sorry. The other term being dv, right, du dx is the same, and the other term being dv dx minus du dy. Right, what is that? Vorticity, right? So again, we are assuming vorticity is equal to 0 to start with. Then this term becomes 0, right? Of course, we can write it down like as a du dy times vorticity, right? But like if vorticity is 0, then the contribution of this is going to be 0. How about these two added together? The common term is dv dy, right? And the remaining is dv dx minus du dy. Again, vorticity or minus vorticity, right? So that actually becomes, the entire thing becomes 0 if omega is equal to 0. Now, how about this? I forgot a square on this. How about this? It's the same, right? If you look at the u term, what we get is u times the x derivative of negative vorticity, right? Or not negative, just u times the x derivative vorticity. If you pull out the ddx term, what get remaining is u dot with ddx of parentheses dv dx minus du dy, right? How about this? We get v times the ddy of parentheses. I get a sign messed up. This is plus. Yeah. V times the ddy of dv dx minus du dy. So again, vorticity. So this basically tells us this entire term is also equal to 0 if we get vorticity is equal to 0 to start with. And of course, the whole thing is equal to 0. That means the partial derivative of vorticity with respect to time is also equal to 0 if you get no vorticity to start with. Okay? And actually, you can derive a little bit more than that, because even if you have vorticity, you can follow exactly the same derivation to see that this term is actually going to be the cross product of velocity with vorticity, and that actually is this term is going to be actually So this term is like a cross product, and this term is actually an advection term. Is u dot with the gradient of vorticity instead of velocity. So basically, what you can derive is really the material derivative of vorticity is equal to 0, right? If you get no, if you get no viscous forces. So this is why there is actually a lot of cases where vorticity is equal to 0, right? In the entire flow field, I mean, if in most of the flow field, if not the entire flow field, it's because the vorticity would stay 0 if it initially is 0. And even if you only have part of the flow field having 0 vorticity, that part of the flow field, as it goes with the flow, will stay with 0 vorticity. Okay, any questions on this? Now, what does that mean if you follow videos like this, right? What it means is that whenever you're looking at an airplane, so the air that passes above and below the airplane has no vorticity to start with, right? And the only part of the flow that gets vorticity injected into the flow field is the air that passes very closely to the body of the airplane, right? So there we know it has boundary layers, and in the boundary layers, the viscous forces cannot be neglected, and there is vorticity generated. But if you follow the air above and below and beyond the tips of the airplane, there is no vorticity to start with, and there is no way of generating vorticity. So you know that even after the flow passes, right, even if you look at this region, most of the flow field has no vorticity, right? There is no vorticity here, although there is actually no vorticity here, although you see the flow moving down, right? Because the air, if you trace it backwards, it doesn't go through any airplane wings. So what you only get is actually, we're going to see later, a tiny fraction of the flow field that, like, you cannot clearly visualize from here, that actually has viscosity. It starts with these two concentrated vortices, and there is really just the flow that passed very close to the wing of the airplane that has vorticity in it. Okay, and in particular, a lot of this vorticity gets what we call rolled into these two tip vortices. So you see these tip vortices being very strong and concentrated. Okay, that's why there is a lot of cases where there is no vorticity in most of the flow field. You can do the same analysis in 3D. So it'll take too long for me to do it in 3D, but like, you can do the same. If there is no vorticity to start with, you get no vorticity in the flow field, assuming you have uniform density and no viscous forces. All right. Okay. And the second is, if there is no vorticity in the flow field, you get a lot of useful stuff. Let me see. You get a lot of useful stuff. Let me just give you one example. Everybody knows Bernoulli's equation, right? In an incompressible flow field, what is Bernoulli's? Well, if you got to the end of homework that's due tomorrow, you should know it, right? Or if you've taken unified. Okay. Anyway, P plus what is equal to constant? 1/2 of rho u squared, right? Or magnitude of velocity squared is equal to constant, and that's what defines the stagnation pressure or total pressure, right, in an incompressible flow field. And in the homework, you're going to be working on, if not yet, pretty soon, you're going to see that in a compressible flow, this is not going to be as simple as this one. You are going to have a lot more complicated formula with the power of gamma over gamma minus 1 and things like that. Anyway, so, but what's often being mistaken by a lot of people, especially of your stage in learning aerodynamics, is when is this applicable and when is this not applicable? Okay. So in the homework, had everybody looked at least the second problem yet? You have? Okay. Okay. So in that context, right, we are pretty sure, right? I mean, it gives one example of when this is applicable, right? What is that example? What? I hear a stream. Free stream, yeah, in free stream it is applicable, but the homework problem is not just a free stream, right? what is the scenario of the homework problem? That's not boundary layer. It's the second homework problem where isentropic. Yeah, isentropic flow in a steady state accelerating stream, right? It's a steady flow, which means if you fix a spatial location, okay, the velocity and density and everything is not going to change, right? But if you follow a flow particle, it is of course going to change because it's accelerating, okay? So in that scenario, the stagnation pressure is constant along a streamline, just along a streamline. If you look at stagnation pressure along two different streamlines, they might be equal to two different constants, right? In the homework problem, we didn't derive at all. Is the stagnation pressure equal or not in two different streamlines? Even if all the assumptions are true, like steady flow, no viscosity, and things like that, right? And in general, for example, if you look at the flow field, for example, it is not in general true for like across, I shouldn't say for, across different streamlines. So for example, P is equal to constant, right? So that means there is no acceleration, deceleration by pressure gradient. But velocity goes like that. Okay, ignore viscosity. Just think about the flow fed in with a higher velocity on the top and lower velocity at the bottom. Because there is no viscous forces and no pressure forces, the flow just goes its own way, right? Cruises with no acceleration, no deceleration, no turning at all. Is stagnation pressure constant across the streamlines? No, right? Because the P is the same, but V is different. So this term is the same across streamlines, but this term is not the same across streamlines. Right? So Bernoulli is not true in general across different streamlines. Unless you have irrotational flow, which means vorticity is 0 everywhere. All right? So why is that the case? I mean, this is clearly an example where vorticity is 0 or not 0? Not 0, right? Because think of what is vorticity? Partial V, partial X, minus partial U, partial Y, right? What is partial V, partial X? There is no V, right? There is no V anywhere. So partial V, partial X is 0. What is partial U, partial Y? Of course, as you change in Y, U increases. So partial U, partial Y is not 0. So this is not equal to 0. And therefore, Bernoulli doesn't hold across different streamlines. But if vorticity is 0 across different streamlines, I mean, if vorticity is 0, then Bernoulli actually holds across different streamlines. And we'll see a little bit later why that is the case. But first of all, let's actually, well, let me just write it. But if vorticity is 0, then PT is the same for even for different streamlines. Okay, so this is just one example of how a 0 vorticity scenario is actually very, very useful. Okay, so again, if you go back to this this case, right? If you look at, let's actually get to the end. Again, if you look at cases like this, whenever you see the flow being fast. Right? Because most of the flow is irrotational. And if you go across from one streamline to another streamline, and if the path has no vorticity in it, then you know that whenever the flow is going faster, the pressure is lower, right? Okay, so essentially that allows you some way to really start to see the flow field, right? By looking at how the flow moves, you can infer the pressure. And actually, if you can start to infer the pressure, you can start to see the high pressure region and low pressure region is going to exert a pressure gradient force to the flow field. And if the pressure gradient force lies orthogonal to the streamlines, it'll turn the streamlines, right? If the pressure gradient aligns with the streamline, it'll accelerate or decelerate the streamline. So basically, you can start to really use these principles to infer a lot of information from a flow field that you wouldn't just directly be able to see. Okay, let me actually give you some further example to consolidate your understanding of what is vorticity. So just imagine there are these two different streamlines, and by drawing this, I only draw the direction of the flow. There is no indication of the velocity being faster or slower anywhere, right? This just indicates the direction. Which of these flow fields are irrotational? What? E?
Yeah, it holds anything about the velocity.
Exactly right. So anybody got the same conclusion that fast? Yeah, it's good, right? So this is a case. This is actually a trick. This is a trick question, to be honest, right? You don't have enough information to say either of these flow field being irrotational or not. So this is actually pretty clear. This is pretty clear because if the flow field is uniform, right? If the velocity is the same across the streamlines, then of course it is irrotational because the partial derivative of not only u but also v with respect to not only x but also y is equal to 0, right? Anywhere. So of course the subtract m is still 0. But if it's the other case I've drawn in the last screen, if the velocity is higher here, slower here, even slower here, even slower here, then you get a non-zero partial u, partial y, right? As you go across the streamlines by varying y, your u velocity changes. So you don't have enough information to say if this is irrotational or not. What's a lot more tricky is actually that case. So how did you reach the conclusion that even in this case, you don't have enough information? Yeah.
For the same reason, you kind of get a big hint that unless you know the velocity, it's irrotational.
Right. Okay, so let's actually construct two different scenarios. Okay, where in one scenario, this is rotational, which means there is vorticity, and let's also construct another scenario where this has no vorticity whatsoever in the flow field. Okay, let's actually get to work on this in groups, and Mohammed, if you can tape some of these onto the board, that would be great. Right. But by the way, just an additional thing. When you are constructing an irrotational flow field, there should be no vorticity except for exactly at the center. There is just the one point where there has to be some vorticity, but everywhere else there shouldn't be any vorticity. Just two scenarios. One scenario, yes, vorticity. The other scenario, no vorticity. Yeah. Yeah.
First try. First try Friday.
Gee, those aren't very dotted lines.
So this is the vorticity case. Add a little mark there.
The no vorticity case is when it just like doesn't like.
Yeah.
I just like have it.
And that's on the
like
hard one too.
ingrained in my
This. Oh.
We should have made it like a rectangle so you actually can tell the difference.
That's why a little line.
Okay.
Is that satisfactory to you?
Oh, what I mean is by constructing a flow field, right? So u as a function of x, y is equal to what? V as a function of x, y is equal to what? Yeah, so what I want is to construct a flow field in mathematical expression. So u as a function of x and y is equal to what? V as a function of x and y is equal to what? So that's what I want the final answer to be. Right, so I do two flow fields, one rotational, one irrotational. So just as an example, in this case, rotational u is equal to y, v is equal to 0, and irrotational u is equal to 1, v is equal to 0. Right, so basically
We need this to turn the two.
No. Yeah.
I'm pretty sure the classic example is like a real
I don't like really understand like what's I mean,
well, it's just like
wait,
you
isn't the classic example just x, u equals y?
Then the flow field would look like that, no? And it's like rotate.
No, think about it. It's like let's say this is right. So then, like, if right here, this would be, this would be one. This would be like 1, 0, right? So the v is just 1, right? Here, this is 0, 1. So.
Oh, it's gonna be on the same spot. It should be on the spot.
I'm overthinking right now. It's hard. How could it?
Here, yeah. And then what? And then we have.
I don't even know if this is right, to be fair. Is it DVDX?
Yeah.
Why?
U is -1. So
Yeah, this is the rotation.
Yeah, this is going to be the rotation.
It's a height.
Rotation.
Like a little more definition.
That's easier.
Oh, dude. Okay, that's alright. Wait, why did you erase the map that you just did to create this rotation? Dude, I swear, I think the other one is that V equals R E theta. Yeah, it's this one.
I mean, can you turn that into like?
Yeah, that makes one. Yeah, you can
Transfer it to the X and the Y, bro.
E theta. Yeah, E theta's that way.
Oh, just two hints. I see a lot of people don't know how to start, right? There are two hints. One hint is you can first concentrate on constructing a flow field whose streamlines are exactly circular, right? Then at least you get one of the two answers. You can check the vorticity is zero or not. So you either get a irrotational or rotational flow field, right? So as long as the streamlines are exactly circular, at least you get half of the question. All right, so that's one hint. The second hint is if you try a polar coordinate, might make things a bit easier.
Shishi, I've been on that way. I'm doing my polar coordinates right now.
Okay.
Yeah.
Oh, good, good.
I'll be done shortly.
Okay.
And right here we have a rotational field right here.
Oh, good. Yeah, that's fast. Okay.
Yeah, well, we know we pay attention in class, Shishi.
Yeah. Okay.
I can't say the same thing about the
Okay.
others.
All right. Okay, so you already got a rotational flow field. Now think about how to modify this to get a irrotational flow field.
I think polar coordinates are better.
Wait, can this just be like?
What is this? Y, it's cosine minus x sine. I'm sure that's it.
Yeah, but it's easy. Only one.
Okay, I think we are approaching the end of the class. So
What if we divided it by R?
I think, well, fortunately, I think a lot of you figured out one of the cases, but I haven't seen any of you figured out both cases yet. Anybody figured out both cases? I just didn't have time to check everybody at the end. So maybe this is going to be some after-class exercise before before Wednesday. If you can figure out both a flow field that is rotational and irrotational, that would be great. We'll start with this case on Wednesday to talk about what is the flow field look like in irrotational flow. Not only the velocity, but also pressure, right? Everything, how things all look. Okay, so I'll see you on Wednesday. And office hour is right now downstairs if you want to come.